بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so let's continue chapter 3 and lecture 2 about the foundation of predictive modeling in data science. And today you are going to learn about how to formulate a predictive modeling problem. And you will take the simple example of polynomial regression to go through the different steps. So far, what we have talked about is the expression and the definition of the risk and how to minimize it, especially when it is empirical and when we calculate it by an average of the loss over a sample of data. Okay, and it's going to measure the difference and the discrepancy between the output y and the prediction j of x. But now the problem is, how can we determine this value? We still didn't determine any time this value. We didn't make any optimization problem. We just defined the loss function. And today we're going to learn on how we can formulate a problem. For example, a linear regression problem. You want to minimize the prediction between the house prices and also their surfaces. Okay, how to build this model, how to optimize this model. And we're going to apply this on the example of polynomial regression, which is just a generalization of linear regression. So a linear regression is a polynomial regression, but with an order of 1. Okay, ax plus b. And we're going to use a slightly different notation. Instead of x, we're going to use u. Instead of jh, and instead of capital J, the capital H, just to better align with this example. And to formulate the parametric optimization problem of polynomial regression, so we are going to consider that we want to optimize an optimal polynomial function, h star, for example, that is going to make the mapping, the relation between these points. So we want to find an optimal function, h star. Okay, based on a training data set. As already mentioned, we are going to train on a data set, on a sample of the whole data set. And you already remember that we need to do a split: training data, validation data, and test data. So we're going to take one of the possible training data to train and try to minimize this loss function, or the mean square error in our case, which is the difference between the observation or the response. This is what we call the response or the observation minus the prediction.
What is UI?
UI, just instead of using x in this example, we're going to use u. So yeah, it's the input. Okay, u is the x, is the input. This is the function j. This is the prediction, and this is the response. And here we want to minimize this value. Now the problem: how do we formulate mathematically the optimization problem? Is the problem clear? Okay, I want you to think about it. Okay, now I have this function, it's polynomial at p minus 1 degree, and I want to optimize it. Okay, working directly on the polynomial function is not trivial, it's challenging. So usually in problem optimization, we want to optimize linear problems, because linear problems can be easily expressed as matrices. And everything in machine learning and deep learning is basically matrix and matrix multiplication or dot product and so on. It's basically matrix operation. So when we have a problem similar to this one, whether in regression or in classification, we will try to come up with a mathematical representation using linear algebra, using a matrix representation on how we can model this. So how do you think we can do the modeling?
Matrix?
Yeah.
Selecting important features.
Okay, so selecting important features. How many features we have in a polynomial function regression problem? For example, in this one, what are the features? So yeah, basically our feature is u. But in this particular case, we will have a feature u square until up minus 1. These are our features. Okay, so we have p features. And these beta are the weights, and these are learnable parameters. They are in the beginning they are random. So if they are random, if you put any input here, for example, the surface is going to give you a random output. It's going to give you a random price. So it's going to be very high. And we want to optimize. So what is the idea now? The idea is to transform this optimization problem into a linear optimization problem. Okay. And we can think about the feature vector x to be equal 1 u. So 1 here, it's because it's going to be multiplied by beta 1. So it's basically x or u power 0. And this is why we made the u representation here, is because we are going to use the x representation as the feature vector. Now, we're not going to talk about a scalar feature, but a feature vector. Okay, so we are aggregating this as a feature vector, and these values are dependent because all of them, they are depending on u. Okay, but since we are representing this as a polynomial problem, for every type of u, we have a different weight. We have a different learnable parameters. Okay, in the simplest model will be just a linear regression. So I'm going to p minus 1 will just p will be equal to 2. Okay, and here I will have beta 1 plus beta 2 u. This is just purely linear. And then I can have quadratic. And then I can have at higher order. And we have discussed the trade-off to do between the model complexity and the simplicity based on the bias and the variance that we want to optimize. Okay, so now we have defined a feature vector, and our problem will be reduced to finding the function j such that j is equal to x transpose, the feature vector transpose, multiplied by another vector beta. So I'm going to create a vector beta 1, beta 2, beta 3, and then beta p. And this will be a vector, and this one will be another vector, and it will be just vector multiplication. And for this particular problem, for example, we can find that for p greater than 4, this is the optimal solution. Now, we want to learn how can we find the optimal solution using this type of representation. Okay, so, and the main concept, as already explained, is to transform the polynomial regression into a linear representation, okay, linear equation. Okay, let's recapitulate right now. Okay, now I have presented the concept of simplifying the polynomial model through feature expansion. We start by a polynomial model representation, and then we're going to define the feature space expansion, okay, which is u. So every u is going to lead to a feature vector equal to this one. And then our problem will be reduced to a linear model formulation in the expectant space. So we try to find the function j of x that is equal to x transpose multiplied by beta, which contains the weights, the learnable parameters. Okay. And the objective here, the optimization objective, is to find beta star that optimize the function j. Okay. So the next step now, we have a feature vector. And usually to work with matrices, okay, we can actually expand the linear problem formulation into a feature matrix. So what does it mean? This is one observation. So this represents one x value, one surface, for example. If we take estimation the price of a house based on the surface, so this will represent only one surface value. But you have multiple points. Imagine that you have 1,000 surface values. I'm not going to put it one by one. This is time consuming from optimization. And usually, we have learned this in Python, vectorized operations are much faster than using for loops. If you are going to use as a list and you use a for loop, it's going to be very computational expensive. You remember the vectorization and broadcasting we've talked about? That's pretty much related to it. So usually we want to aggregate our input as a matrix. And this is usually, we call it as a batch. So you have one observation or one what we call input feature vector, and you are going to organize it into a matrix representation. Of course, the larger the matrix, probably it's better, but you have also other constraints, like for example the memory. If you have terabytes of data, you cannot put everything into one matrix and put them into the memory. So usually we need to subdivide into small batches, smaller batches that can fit into the memory space of your whole memory and also into your GPU memory when you train. So these are some practical constraints. But now we assume that we can organize our data as a feature matrix X. Okay. And this represents one observation. So I'm going to present many terminologies that are pretty much used in every predictive modeling. Understanding these terminologies is essential for you to understand all the different operations that we are going to apply on this. So the first terminology this is called a feature vector representation, and this one is called a feature matrix representation. And basically a feature matrix, it's beneficial for multiple purposes. So this could represent a batch of data. It can be the whole data set if the data set is not very large, but usually we are going to subdivide it into a batch of data of size n multiplied by p. So what is n here? Okay, so n, we have n observations. This is one observation, second observation, nth observation, and I have p features. First feature, this is the first for beta 0, beta 1, beta 2, and beta 3, and these are its corresponding numbers.
When you say u or u squared, you don't mean you are squaring the u. It's a different feature.
Yeah, the u, for example, think about the u is the surface of a house. It's the same value.
So in xi you have the surface of the house.
No, xi, it's a feature vector. Now, if we take the simplest problem, think about these points, surface of a house, and this is the price. Okay, so this point is u, and it will lead to a feature vector 1, u square, u cube, and u the power. It's one feature. One feature will be a vector, because here we're not making a linear regression, we are making a polynomial regression. Okay?
You're expanding the feature.
I am expanding, the same feature is expanded because it will be weighted to different numbers. Okay? They are not different numbers. It's only one u. Okay? So it's the same input, but it will be expanded according to the polynomial order. Yes, the length of the polynomial, or the order of the polynomial, or the degree of the polynomial. Okay, so this is how we do it. Okay, so this is one feature, this is one point. Okay, this is one point, this is another point, this is one point. One point is represented by a feature vector. Of course, in other type of feature vectors, maybe these features, the values inside the feature are independent. Okay, مثلا, I can use a feature vector that contains the surface of a house and the number of rooms, and also maybe the location. I can have a feature vector like this. But this particular case, because this is a simple regression problem, polynomial regression in two-dimensional space, okay, so the feature vector contain only one feature, but expanded over different orders. And this is the benefit, represent multiple observation at a time, and this actually facilitates the prediction and also facilitates the computation, and to make the computation faster and more efficient. And let me explain you here. Okay, so in this particular representation now, again, this is my data, and now here I have a polynomial regression of order of degree 2, second order. So beta 0, beta 1, and beta 2. Okay, look, this is a very illustrative example, and this is my equation. It's beta 0 plus beta 1x plus beta 2x squared. So this is, okay, so this is the feature x. It has 1, x1 squared, and this is what I have here. And this value, what do they represent? They represent actually beta 0 plus beta 1 squared will be this one, and So this is the first observation. This corresponds to one of the points here. Okay? Now this is another point. And this is another point. So here I have 5 observations. Okay? And the degree of the polynomial here is 2. Okay? And look now, if we look from the degree perspective or from the feature perspective, this is the feature. These are all the observation for feature beta 0. These are all the observation for the same feature beta 1. And this is the all observations for the feature beta 2. Okay, so the first column, this one, is the interceptor. This is because x is at the power of 0. We don't have x, so this is what going to intercept. And then the second column, the predictor, and the third column, x square capturing quadratic relationship for this particular. Okay. And you know, these are the coefficient of the optimal. Now, these are the coefficient of this red curve. This is based on the training that we have done on this data. And this is a possible value. You cannot say it's the optimal value because it's empirical. It's based on only one training data. It's an empirical coefficient for beta 1, for beta 2, and for the intercept. Any question here?
How do you get the line?
Yeah, here I have run just a machine learning based on this training data set. It generated this one with this corresponding value. But the objective is not about that. The objective is to explain you the difference, how to represent data in a matrix, and the difference between observation, which is one row, and the feature, which is one column. Now we are talking only about definitions, and taxonomy is used. So later on, when I go further, I talk about the optimization, I talk about the feature, you know what it is, because it might be confusing. Okay, like you have validly questions about why we have here the same value, okay, or whether it is a different value, but this represents only one feature. But this is very particular to the polynomial regression problem. In other type of problems, they can have a feature vector with completely independent parameters. Independent, but they affect the response, the output. Okay?
Doctor, usually, do certain models get complicated and take high degrees of polynomials?
Yes. Now, this is a machine learning model with 3 parameters. If you talk about ChatGPT, it's a machine learning model with 75 billion parameters. And you know, all these parameters are just numbers. It's just numbers. A parameter, when we say 175 billion parameter, it means I have 175 billion numbers that represent the weight of the model. But of course, the model, it has an architecture. And the architecture, it means it has different types of operations. Now, this operation here is just linear. Okay, I'm going to concatenate, okay, the different weights with the power of the feature. But other models, they can do, for example, we have self-attention, they can do relationships between different features inside the same data. Okay, there are convolution in images, for example, to extract the features. A recurrent neural network, they have a different type of operation. So later on, we will have different type of machine learning model, but all of them, they will try to calculate similar weights that will minimize a loss function, a risk. Same what we talked about in the previous lectures. Okay, but now just on this very simple problem, you understand. Now this is a very basic, simple machine learning problem with only 3 parameters because I don't need to have much more complicated problem. Yes?
The 175 billion is rows or columns?
No, it's a very complicated architecture. I mean, there are many modules, you know. There is linear layers, there are self-attention layers, there are multi-head attention layers, there are different normalization, batch normalization. It's very complicated, but we are going to go to that step by step.
They use supercomputers to develop.
Of course, yes. You need
165 billion.
Yeah, it was trained on 10,000 GPUs. Yeah, $5 million cost of the training. It's not easy. Not everyone can do it. Yeah. So this is a model. Now I want you to understand what is a model. When we talk about a model, don't think about something magical. It's just a collection of numbers that we have optimized to minimize a particular loss. Our loss here is what? Is the mean least square error. Okay, so this actually optimized the least square error between this point and this model. That's the whole study. And we need to find these numbers, okay, beta 0, beta 1, and beta 2, and this represents a machine learning model for this particular use case. It's as easy as this. Let's try to complicate it a little bit. And now I can try to derive a machine learning model of degree 4, and this model will have 5 parameters. 5 parameters, beta 0, beta 1, beta 2, beta 3, and beta 4. So imagine that you have y is the house price, x, this x is the surface area of the house, and this is x squared. Now, what's the difference between this one and this one? This one tried to find a quadratic relationship, and this one saying probably there is a more complicated relation. Let's try at the degree of 4, whether it can have a better loss function. Okay, so this model, look, it has 5 parameters. This is the optimal parameters. The red represent the second degree, and the blue line represent the 4th degree polynomial regression fit. Okay, and what's the difference now is about how the data is represented. نفس الشيء, we have here one observation, second observation, and how many features I have? I have 5 features. Every column is a feature. Okay, simple. And we have this epsilon error. This actually represent the noise or the error term that accounts for particular deviation from the model. And that's how it is represented. These are the first data points that you use for training. Okay, these are 4 data points. Okay, let's move forward. Now, what is our problem? The problem is to find, is to optimize the polynomial regression problem such that to minimize a training loss. So what is a training loss? We are going again to have another vector which represent the output for every feature. Look now, if I go here, for this observation, I have the output y1. And for this one, I will have the output y2. Okay, is it y0 or we start from y1? Okay, usually we start from y0. Okay, now you will have here y1, y2, y3. Every feature will correspond to a particular output. And now we would like to find the vector beta that's going to produce the closest value to the output, y1. And how to make sure about this? We're going to define the training loss as the average of y. This is now all the observations, and these are all the predictions. So yeah, so the prediction here, beta, is going to be random in the beginning. So of course we will have a training loss that is high. And later on we are going to optimize by using derivative with respect to the feature vector. With respect to, okay, not to the feature vector, but with respect to the beta. With respect, so we will see these derivatives later on, but let's first understand the problem statement. Okay, and now we have y is the response vector, x is the feature matrix, and look now we will have kind of vectorized, we will have a vectorized representation. We have y, it's one-dimensional vector, minus x, it's n multiplied by p. Yes, and beta is one-dimensional matrix. So we have a dot product. Okay, so this one is going to lead to a vector of the same shape of y. Now we talk about the shape. Okay, so understanding the shape is very important. We will have a complete focus on calculating the shape, especially when we do that on Python. Okay, واضح الأشياء. And even I try to link with Python in terms of vectorization shapes, because these shapes must match. I'm going to find a one-dimensional vector such that I will compare y1 with j1, which is the expected, okay, or the predicted value. And we want to minimize the sum of all errors. Look here, I put the norm. It can be also the sum, okay, the sum divided by n, which will be the average. And to minimize the training loss, achieving the best fit between predictions and observed data. So this is a problem formulation. It's a complete lecture about problem formulation. It's not something we need just to outlook, because formulating the right problem is the key to the success. And it's even more difficult to training the problem itself, because any mistake that you do here in terms of data representation, definition of your loss function, you're not going to lead to a successful study. Okay, so just to summarize, we started from a polynomial regression equation, and finally we come up with finding the training loss, and our minimization problem is to find the empirical optimal coefficient vector beta such that it minimizes, what's arg mean over all possible betas, that will minimize y minus x beta. And this is the first time that we are putting here an explicit function. بل كنا نعمل g of x. Now this is our j of x. It's x, yeah. This is the problem formulation, is try to find a possible family class. Now the family class that we have chosen here, it's the polynomial family class that we can try. Maybe we can find at the first order, the second order, the third order, or the nth order. Okay. So identifying the best value of beta vector is crucial to enhance the model predictive accuracy. So let's observe right now how the loss variates. Now we've built actually this regression problem. Imagine that you've built this one. And look at the Python code here. I have taken beta 1 optimal and beta 2 optimals. They were calculated. Okay, let me just show you here on the notebook. Okay, I start from here. Look at this example. So we start by hypothetical model, which is equal to this one. It's quadratic relationship noise. Okay, so this is just to generate some random data. And here we are going to create a linear regression. This is the training. Don't focus about this because we will learn how to train later on. But we trained here, and finally it will generate what? Now this is the trained model, and this is our data, and I want to find the coefficients. Let me check. Let me show you the coefficient. These are our coefficient. This is beta 0, this is beta 1, and this is beta 2.
CoF is a function.
Yes, and this one the same but at the degree of 4. This is the intercept, beta 0, and these are the other beta. Okay, this one was made for degree 4. Okay, look, here I have degree 4, and I have the degree 2, the above one. Okay, and then you have both of them. So these are the coefficients, the optimal coefficients, and this one is the optimal coefficient. Now, when you see here, beta 1 optimal coefficient, this is for the second order. So I have calculated them, and they are available at coefficient 1 and coefficient 2. Okay.
Doctor, you mean these are the observations or?
No, we have beta 0 plus beta 1 x plus beta 2. The coefficients are beta 0, beta 1, beta 2, okay, until beta 4 if it is.
You took the first one and the second one, right? First
I took
one,
degree of 2 and degree of 4.
Oh, you took the degree of 2 and degree of
Yes, yes. So look now, in this notebook, this represents the coefficient at degree of 2,
Yes.
and this represents the coefficient at the degree of 4.
So you took
And
four.
yes, and intercept, when I say intercept, is beta 0. Okay? And these are the coefficients for x, x squared, x cubed, and x at the power of 4.
What's the coefficient of x?
Huh?
Coefficient of x.
Coefficient of what?
This for x.
This is the coefficient of x. This one. This is the coefficient of x squared. This is the coefficient of x cubed. And this is the coefficient of x at the power of 4. Okay, but now what is more important? Okay, it's what I have here in this plot. Now, I have found the coefficient of the second order polynomial, which are optimal. And now we've done an experiment. if I fix beta 1 optimal in this equation, look, this is the equation, beta 0 plus beta 1 plus beta 2 x power 2. You've seen this one? So what I'm doing here, I am fixing the optimal values of the intercept and beta 1 and changing only that of beta 2. And this is the curve, look. This is the curve that we can get. This is the variation of beta 2 if we fix the optimal values beta 0 and beta 1. I want to show you something. So what is the minimum value? It's at this point, right? So this means that for the optimal values of beta 1 and beta 0, if the value of beta 2 is at around -2, I have the optimal polynomial function. Look now. When we solved the problem, we found that beta 0 was 0, صح ولا لا? Okay? And this one 3.04.
Yes.
And this one minus 1.93. What is minus 1.93? It's this value. Look at this. Minus 2.5. So I am here at almost -2. This represents for a fixed value of beta 1. I'm going to show you when I change both of them. But just for you to understand the optimization problem. The optimization problem, it's finding the lowest possible point that will minimize the loss. This is the representation of the loss. Look at the Python code. I am calculating the loss. I am calculating the prediction, then calculating the loss for that prediction. You see what I mean? When you calculate a prediction, I want to, okay, so this is y predicted, and this is the difference between the real value and the predicted value. So I will calculate this for a couple of points.
Yes, it's the function we saw.
I will calculate this for a couple of points, and this will lead to a curve like this. This is the curve for the loss, look. So this means the loss can be high or can be low based on the value of beta 1, beta 2. We found that, and this confirms the optimization that we have done. For this value, the lowest value corresponds to the optimal beta 2 value. And the machine learning, it tries to find not only beta 2 optimal value, but beta 2, beta 1, and beta 0 that will make the loss to the lowest part. Okay, and now our equation will be, it must be 0 here. I don't know from where this, the intercept, yeah, I'm sorry, yes. This is the intercept. 3.73 plus 301 minus 1.93 x squared. Okay, and you have observed now what I've done in the Python code. I have fixed this part, and I have tried the loss for different values of beta 2. So minus 193, it corresponds to the optimal or empirically optimal J function, predictive function.
But you're assuming that 3.0 for beta 1 is optimal.
Of course, and I know I find it in my optimization. This is just to illustrate you on 1 degree of the parameters. I only varied only one parameters, just to illustrate you that how to optimize on one parameter. But the optimization is much better. Let me show you on 2 parameters. Here I have changed both beta 1 and beta 2. I only fixed the intercept. So I have a two-dimensional plot. Look now, I did a 2 for loop. One for beta 1 and the second for beta 2. So here I am trying different values of beta 1 and different values of beta 2. This leads to this curve. So the optimal value should be something on the lowest. So the machine learning algorithms, they try to explore all this loss function and they try to minimize it. And they minimize it using the derivative. And the derivative, when we talk about matrices, it's called the gradient. And we call it the gradient descent. It's basically, we have curve like this and it's going to descend until finding the lowest point. In this particular case, that's pretty much simple because you only have one slope. So you will find yourself in the middle. But some of the curves, they can have up and downs, and you can have different type of minimums. Some of the minimums are local, some of the minimums are global. We will talk about this in convex optimization. Yes, yes. That's pretty much simple. Okay, it's just simple two-dimensional curve or three-dimensional curve that you need to optimize. And the gradient descent will try just to move until it reach the best point possible. مثل bull eye اللي اتكلمنا عليها. You try to shoot over that. Yes. And look now, after we find out the optimal parameters, we say if we change these optimal parameters just to explore the space of the loss. Now, this represents the space of the loss function. If you choose any values now, if I do gradient in two-dimensional space or three-dimensional space, these values are going to descend until coming to some point here in the lowest part. The lowest possible. You see? Okay? So this is the optimization problem from high-level perspective and how we see it from the loss. Okay? We didn't talk about the mathematics, but this is just a Python illustration about how things can go down. Okay. Does this make sense? Don't worry about it because we are going to go through many examples, but this is like the core concept about how we do optimization. Of course, there are mathematical formulations that helps you to do the gradient, to calculate the derivatives, and find out the mathematical formulation that will illustrate this Python plot. And basically, we can show it in two-dimensional. Okay? So, originally, your loss will be somewhere here. Maybe here. And then with the gradient, it will go like this. Okay? Sometimes up, sometimes down, sometimes up, sometimes down, until it reaches. Maybe not the optimal, but if it is something around, that's fine. Yes. Think about the bull eye problem that we talked about. The bias, the variance. Now, if you have a lot of bias, or if you have a lot of variance, you can find yourself either scattered here or probably focused on a very located place. You see, things are related. Okay, now we see this on real examples. Okay, and that's pretty much it for today.